So, we begin with a new lecture again. So, this is again on a structure of non-crystalline solids, mainly glasses. We will continue from the previous lecture we were. So, let me just give you a recap of what we discussed in the last lecture. We basically introduced the term called as non-crystalline solids. Basically, these are the materials which do not have any long range periodicity. The periodicity of molecules in the form of any kind of periodicity, let us say spatial periodicity, it exists over very short ranges, few nanometers, and beyond that it breaks down. So, if you go to few tens of nanometers to hundreds of nanometers and microns and so on and so forth, you do not see any periodicity in the crystal structure. So, as a result they do not have long range periodicity. Another thing is that they do not tend to have fixed bond lengths, they tend to have variable bond lengths, which allows them to have multiple bond energies, and as a result they tend to solidify over a range of temperatures, and hence they have a broad and diffused melting behavior as against crystalline materials, which show a very sharp melting transition at the melting point. So, and by and large these materials are based on the basic building block is silica, and it is by the arrangement of the silica molecules within the structure which allows them to have very specific structures. So, we looked at last time, the first structure that we looked at was crystalline silica, in which the hexagonal array of silicate tetrahedra forms. So, silicate tetrahedra, if you recall, it was basically SiO4 4 minus tetrahedra, because each silicon atom is coordinated by 4 of these oxygen atoms. So, if this is oxygen, this is silicon, and then you have the bonds between these, and this basically makes a tetrahedra. If you connect these atoms here, okay, so this basically makes a tetrahedra, and at the center of tetrahedra is this silicon atom. Since it has this -4 charge on it, it is not electrically neutral. As a result, it needs to have either sharing of oxygen atoms to ensure that there is overall electrical neutrality. So, one way to do that was to make a hexagonal network in which you have a corner sharing of atoms. So, the structure that we drew last time was, you had a structure like that, okay. Right, and so these are all polyhedras arranged in such a fashion. So, they make a hexagonal network. Okay. So, it is yeah.
So, how does electron neutrality will achieve?
So, you have one shared here, another shared here, another shared here, and another one shared on top, all right. It is a 3-dimensional network. It is not a, so what I am showing here is in 2D. So, each corner is shared between, so each corner is shared by 2 polyhedras, okay. So, what you will have is basically SiO4, so 4 divided by 2. So, basically you have these are SiO4 units, and for each of them shared between each corner shared between 2 polyhedras. So, what we see here is in the plane, but it is shared out of plane as well. So, this is the top of this polyhedra, for example, this is going to be shared by the top one. So, 1 here, 2 here, 3rd here, 4th here. So, Si is at the center, O4 divided by 2, it is going to be SiO2, right. So, this is the crystalline form. Which has this hexagonal array of polyhedras. Now, second, another thing that you can have is you can have amorphous silica. Now, amorphous silica will be present in such a fashion, so that you have these polyhedras which are present more or less in a sort of random fashion. Okay. This will have somewhere here, it will have another network. There is no fixed angle and there are no fixed number of neighbors. Now, the problem here is the electrical neutrality again. So, in order to have such kind of random network, this random network is possible only when the corners are shared by something else. So, that there is something electrically something which is electrically neutralizing it, and this happens by addition of impurities. So, when you add, for example, you can see that in the previous structure you had the 4 corners shared by neighboring polyhedras. In this case you do not see a neighboring polyhedra, right. You see that this may have a sharing, but this will not have a sharing. So, what happens in this cases is you attach the what we call as functional groups or impurity oxides. So, for instance, if you have let us say SiO4 4 minus, instead of sharing with 4 polyhedras, you are sharing only with let us say 3 polyhedras, right. So, silicon is all right, this oxygen is shared, this oxygen is shared, this is shared, but this is not shared. So, which means there is an extra charge. Okay. This extra charge is going to be compensated by, let us say, if you have an impurity with it. Okay. So, for example, you can have sodium plus, potassium plus, some of these impurities will attach to that group and they will ensure that they will take the extra electron that is there, because these are all electropositive elements. So, they will attach themselves to those groups, forming structures which are electrically neutral. So, this will make, so things like K2O, Na2O, CaO, variety of elements can get into the structure of glass, modify the structure in such a fashion so that polyhedras are not any longer shared by in such a fashion, so that each oxygen is shared by 2 polyhedras. So, they make a random network sort of thing. So, a good image of this would be, I will show you in the PowerPoint. So, this would be sort of the image that you would like to see. So, this is amorphous silica, but in this case again electrical neutrality has to be maintained, and the electrical neutrality is going to be satisfied by presence of some sort of neutralizing factor, which could be impurity, basically to neutralize the charge. So, there are a variety of forms of silica. Let me now show you how it happens. So, if you have this So, let us say silica structural units can be presented in different ways. Okay. So, let us say the criteria is how many numbers of oxygen ions which are shared. Okay. That is the first column. Structural unit, then we will, second is the structural unit, and then we write what is the structural formula. Then we write what is the charge balance. Then finally, let us look at the example. So, you see from the previous slide, the key thing is how do these unpaired electrons or imbalance, charge imbalance gets accommodated, because it has to be electrically neutral, that is the bottom line. So, how does it get to do that? How does it do that? So, the first thing is, let us say number of oxygen shared is 0. So, in this case the structural unit will be 1 tetrahedra, just 1 tetrahedra. It is not going to, if there is no sharing, which means it is going to remain in tetrahedral form. So, this is basically island kinds of structure, island sort of SiO4 kind of structure, and here you can see the charge balances. Silicon is going to give you +4, oxygen is going to give you -8. So, the total charge you are going to left with is -4, sorry. Yeah. This structure where there is no sharing of polyhedras is followed by materials such as, these are called as olivine structured materials, basically Mg iron twice SiO4. So, you can see that there is attachment of these magnesium and iron atoms which fulfills the charge neutrality condition. Okay. So, these are cations which are looking to pair themselves with the silicate polyhedra, so that the extra charge, that is -4, is taken care by magnesium iron. So, it could be 1 magnesium 1 iron Fe2 plus, basically it could be 2 magnesiums, it could be 2 irons. So, it could be Mg2SiO4, it could be Fe2SiO4, or it could be 1 Mg 1 Fe SiO4, and if both of them are in +2 charge state, then you can have any fraction of them. Okay. It could be Mgx Fe1 minus x if both of them are +2. So, they will make it charge neutral by attaching itself to the corner of the polyhedra. So, this is essentially a olivine structure, a sheet like structure. The second structure in this category would be when the number of shared oxygen atom is equal to 1, and in this case you have first polyhedra like that, second polyhedra like that, like this, all right. So, in this case it makes basically again, so in this the first structure was ortho structure, and the second case it is again an island kind of structure, because it does not make a structure which is continuous in 3D, because you do not have complete sharing. So, here it makes Si2O7 6 minus. So, basically silicon will be +8, oxygen will give you -14, and net will be -6, Si2O7 molecule. This is called as pyroform of it, and these materials are basically for example hemimorphite. Hemimorphite whose structure is Zn4 Si2 OH twice dot H2O. This is for example an example. This is a case of one sharing of 1 oxygen atoms in the polyhedra. Not very common, but there is an example. Third one is called as 2 sharing of this So, this is in this case what you have is a single layer of SiO3, these are 2 minus. So, basically what you will form here is a chain, or so you will have this kind of structure. So, you can see that you have 2 neighbors only, it has just a chain like structure, no 3D structure. So, just shared along these 2 sides. So, this is SiO3 single layer, you can have this kind of structure in which it will make a hexagonal sheet, just a single sheet structure. Just a single sheet, okay, and this is basically called as chain ring molecule, which is SiO3 2 minus, again only 2-fold sharing. Okay. So, in both these cases the net charge is equal to, you can see that silicon is +4, oxygen is -6, net is -2, and this is followed by compounds such as MgSiO3, Be3Al2, SiO3 6. Some of these compounds follow this kind of structure. Other examples that we include, how many columns we need to draw? 1, 2, 3, 4, 5. They are not, they cannot be crystalline. Some I mean you have a pattern, but how does this pattern repeated into the 3D? You have only one, for example, there is no corner sharing here. Okay. In this case also there is no corner sharing, there is only one corner sharing. In this case it is only 2 corner sharing. So, they are all semi-crystalline structures. Now, let us look at this. So, now let us look at what is the next one is. Next one is interesting, we call it 2.5 sharing. So, what happened in 2.5 sharing is essentially you have this kind of layer. Let me just move this. Right. Something like that. Okay. So, you will have just let me draw one more polyhedra. So, it has 3 of them are sharing. So, you have one guy shared here, another guy shared here, and this guy is shared here. So, this is called as a, we call it, just for the sake of calling it, it is called as 2.5 sharing of polyhedra or oxygen. This is called as double structure, which is based on Si4O11 6 minus. So, the charge balance in this case would be, you can see that silicon will be 16, oxygen will be -22, this will be -6. So, for example, minerals such as tremolite, asbestos, they follow this kind of sequence. So, these are basically 2-dimensional sheets, there is no 3-dimensional pairing in this case. just a two-dimensional sheet like structure. And then we have the so in this case the pairing was only in this direction, there was no pairing here. So, no pairing here, no pairing here. So, effectively it works out to be 2.5, because some of them are paired in 2, some of them are paired in 3. So, effectively it works out in 2.5. So, the three-fold shearing is in this fashion. As we, so if you continue this, the same structure that is present up. So, for example, you have this, 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 so basically it's allowed to be paired in, it's allowed to be paired in this direction, this direction, this direction, and in this direction, but not in the vertical direction. Okay. So, this would be, you have to draw these lines, right, otherwise you would miss out on the top bond. Okay. Similarly here, all right. So, in this case the y direction pairing was missing and this was missing, there was no top bond, all right. Here only the top bond is missing, the XY pairings are there, and this structure is called as basically a sheet like structure. Sheet like structure, it is Si2O5 and this will be 2 minus. So, Si will be, you can see here, plus 8, oxygen will be minus 10, net will be minus 2. You can say Moscow white or mica, you might have heard of mica. This basically compound is KAl2OH twice I3Al O10. So, complicated form, a sheet like structure. Okay. And then the final one was the 4 pairing. Okay. As we saw in the first slide, you have 3D network of SiO2 tetrahedra, and this is basically SiO2 4 minus, basically SiO2 0. Okay. So, you have here Si will have 4, oxygen will have minus 4, net will be 0. So, this is basically a crystalline silica, which is called as quartz. So, these are various forms of silicate solids that may occur depending upon how the oxygen is shared between the tetrahedra. So, there is a whole variety of these materials. So, this is, for example, a representation of 3D random network of silicate tetrahedride fused silica. Fused silica is amorphous. So, these are all you can see that you have 6 polyhedras, but they are all at random angles, various possible coordinations. So, at some places the silicon distance is longer, at some places the silicon distance is shorter. So, it does not have regular periodic arrangement. Basically, this kind of thing is achieved by adding impurities, and these impurities basically lower the softening temperature of glass, which otherwise is very high. And if softening temperature is very high, you cannot mold the glass into a shape which you require very easily, and that is why one adds these impurities like sodium oxide, potassium oxide to the glasses, so that one is able to achieve the required level of softness to the glass to be able to mold them in various shapes. So perhaps we can wind up this lecture here very quickly. So basically what you do is that you have impurities in the glass, and these are basically added to modify the or softening temperature. So for example, if you have a structure like this, okay, this is how tetrahedra are shared in certain structure, okay. Now this is shared at the corner. If you add sodium to it, for example, what it might look like is you may have a tetrahedra like this, which is attached with one sodium here, and you can have another tetrahedra which can remain attached with itself with another sodium atom here. Okay. So, they will become loose tetrahedras by breaking of this bond between. This is the bond which gets broken by addition of, for example, sodium. So, this is, you can say, sodium is a glass modifier or it is a network modifier. So, this is how it is going to change the viscosity of glass, for example. Same purpose is achieved by adding various other elements, which we will look at in the next class. So, basically in this class we have looked at variety of glasses, the structures of glasses, and the way oxygen is shared between various polyhedras to develop into various structures in glasses. Okay. Thank you.